the absorption. Last time we talked about the refraction R and reflection R, right? Today we are going to talk about absorption. The last topic in the optical properties in the chapter 8. Chapter 8, optical properties. Well, we discussed that in order to absorption happen in a solid, three conditions has to be met, right? The number one, we have to have electrons to be excited in the valence band or in the conduction band, whatever, wherever. We have to have some electrons to be excited. And we have to have empty state for the excited electrons to occupy. And we have to have enough photon energy to excite the electrons. Okay, these three conditions has to be met for the absorption happen in a solid. And the typical semiconductor, semiconductors. If you plot the absorption coefficient with respect to the lambda, so that this is a low energy h bar omega photon, and this is a high h bar omega photon, right? The high frequencies, it's the low frequencies. Then what's going to happen? We're going to have something like this, okay? And this is a number one, let's say number two, number three, number four, and number five. We can distinguish these 5 sections in the absorption constant. And number one is a direct transition. Band-to-band transition, I'm sorry. This got to be band-to-band transition, okay? And then number two is the exciton. And number three is imperfection. The absorption due to imperfections, absorption due to the exciton, absorption due to the band-to-band transition. Okay, and the number four is the rest Strahlen absorption. We have seen this. And number five is a free carrier absorption. And this is important in a metal, of course. The semiconductor and an insulator, we don't have enough electrons to for the light to be observed by the free carriers. We don't have enough free carriers. So we typically have this 5 absorption phenomenon in the semiconductors. And the band-to-band transition, we're going to have a direct and indirect transitions. if you look into the EK diagram, if the EK diagram, the band structure, if it shows something like this, which means the maximum of the valence band and the minimum of the conduction band energy is lying on the k equal to 0. So the easiest way for the electrons to be excited, the shortcut, is from here to here, right? So in this case, we're going to have a direct transition. Or if you have band structures like this, but if some of the conduction band has been filled with the electrons, then direct transition can happen this way, right? So that's the direct transitions. And the indirect transitions, happens when if the EK diagram of a certain solid shows the minimum offset from the k equal to 0, that is the conduction band, and this is the valence band. In this case, the electrons is going to excited to the minimum of the conduction band, and in this case, we going to have a delta K here. Okay? Or in if we have just like that, if we have a partially filled conduction band, then the electron might excited to the empty state here this way. So in this case, we are going to have indirect transition too, right? Well, direct transition, it turned out that the absorption constant is proportional to square root of h bar omega photon minus band gap. Okay? So if you plot the alpha with respect to, if you plot the alpha with respect to the photon energy in the direct transition case, you're going to have a straight line, right? And then here, this is the band gap of the material. This is one way to decide the band gap of the solid. In direct transition case, alpha is proportional to the h bar omega photon plus h bar omega phonon. In the indirect transition case, we have delta k change in the k with the wave number, and then this wave number is consisting of mainly the phonons, okay? And the indirect band gap square plus h bar omega photon minus h bar omega phonon minus band gap square times e to the h bar omega phonon over kt. And this whole thing has to be multiplied by ft, where ft is e to the h bar omega phonon over kt minus 1. All right? So this part is related to the absorption of the phonons, and this is the emission of phonons. So if you plot that square root of alpha with respect to the h bar omega photon, okay, in indirect transition case, then in a high energies, the emission of the phonon is going to dominate the whole absorption constant, so that we are going to have a straight line dominated by the emission. But as you decrease the photon energies, then this absorption of the phonon dominates the whole structure, so that it is going to have different slope. Something like different slopes, something like this, okay? And that is absorption. Dominate whole absorption of a phonon will dominate the absorption phenomenon in the solid at the low photon energies. So we have two cross sections, h bar omega 1 and h bar omega 2. And here the h bar omega 1, h bar omega 1 is going to be indirect band gap minus h bar omega phonon. And h bar omega 2 is going to be indirect band gap plus h bar omega phonon. So we can get the indirect band gap if you measure this experimentally. Then we can get the band gap is going to be 2 divided by h bar omega 1 plus h bar omega 2. And the phonon energies involved in this absorption also can be deduced by h bar omega 2 minus h bar omega 1 over 2. So these two parameters are very important in a solid. The indirect band gap can be determined in this fashion, and then the phonon energies which can be involved in the absorption process of the solids can be obtained by this measurement, especially if you can determine the h bar omega phonons. Okay, then I just erased. If you know the dispersion relations, omega versus k of the solid, and then let's say that photon energy is corresponding to this, okay? That is the h bar omega phonon, okay? Then you can determine the k values. And this k is going to be the delta k in the band diagram of, let's say, if it is an indirect transition, and you know we're going to have a delta k happens in this EK diagram, and that delta k can be determined by the measurements there, so that we can draw all the EK diagram of the solid. Right? So this is one way to draw the EK diagram of the solid by measure the absorption coefficient or absorption constant of the materials. Now, what about the degenerate semiconductor case? Degenerate semiconductor means, let's say, degenerate semiconductor. What does that mean? It means that this is the conduction band and this is the valence band, and the Fermi level in a typical semiconductor should lie in between this band gap, right? Somewhere in between the band gap, the Fermi energy should lie in a typical semiconductors. But if you have a degenerate semiconductor, it means that the Fermi level now is sitting above the conduction band, something like that. So that in a typical semiconductors, the occupancy, the probability of electrons to occupy that energy level should be half. And that is the definition of the Fermi energies. In a metal, the Fermi energy is can be defined as the energy that free electron can have, the maximum energy. That is the Fermi energy in the metal. But in a semiconductors, the Fermi energy can be defined as the half probability of occupancy for the electrons. That is the definition of Fermi energies in the semiconductors. But if the semiconductor is degenerated, it means that the Fermi energy lying above the conduction band, and EK diagram, if you draw this in the EK diagram, it means that the electron is partially filled on the conduction band. So in this case, we have two ways for the electrons to be excited. One is this, which is the indirect transition, because it accompanied with the changes in the K values, or this electron is going to be excited to this empty state, and that is the direct transitions. Both has both are possible for the optical transitions. In any case, that's happened in the degenerate semiconductors. So if you have a semiconductor and it can be transformed into degenerate state by heavy doping, for instance. If you do the heavy doping, then the semiconductor becomes metallic. And then this semiconductor is going to be called the degenerate semiconductor. And otherwise, it should show the direct or indirect transition. But once it is become a degenerate semiconductor, then we have two ways, one or two. And or this one and this two has almost the same probability to happen. For example, in the number one indirect transition, it should accompany with a change in K values, so it has a very low probability for the optical transition to happen. And for the number two, the most energetic electrons is not going to be involved in this transition, even though it does not accompany the change in wave number, K values. So it has, may have a higher probability for the optical transition, but the electrons involved in this direct transition is not the most energetic electrons, so that the probability reduced, so that the probability for number one to number two happen is almost the same in the degenerate semiconductors. Well, so in band-to-band transition case, typically the absorption constant is more than 10 to 6. Absorption constant is 10 to 6. Now we have to talk about the excitons, and it's about the 10 to 5, less than 10 to 5. The absorption constant for the excitons is less than 10 to 5, and then the exciton is if you have not enough photon energies, then what's going to happen is that this is conduction band and this is the valence band. But in some covalent materials, if the material has a covalent bonding, then it means that its bonding energy is very high, okay? And in that case, this electrons and the hole pair can happen, and then with the Coulombic attraction, it can live like that for a couple of seconds. Even it can extend it to minute levels. Then absorption can happen in the solid accordingly. Okay? So in this case, this is a plus minus charges coupled, so no net conduction happens. No net conduction. No net generation of electron or hole, right? So it means that the photoconduction zero. There's no net charge transfer with this light absorption. In a band-to-band transition case, you are going to create a hole in a valence band and free electrons in the conduction band. So if band-to-band transition happens, we do have increase in the conductivity of the material because we increase the number of free electrons by the excitation of the electrons in the valence band. However, in the exciton case, it is coupled, the electrons and holes are coupled together so that we do not have any net generation of electron-free carriers, okay? So no photoconduction can be observed in the exciton absorption. And this exciton can live for a couple of seconds and the minute at most, but after that it's going to recombine. This electron is going to fall down to be captured by the hole, or is going to diffuse away out of the solid, okay? Or even it can be ionized. In that case, we are going to have a net increase in the conductivity. So it has three ways for these excitons to move after the absorption of the light. One, diffuse away. Second, it can be recombined. And thirdly, it can be ionized to create the electrons and holes in the conduction band and the valence band. It has three ways. It has a choice. But most of the excitons is going to recombine after certain lifetime. Anyway, once you have this exciton, okay, the exciton energies, as you can see in this figure, we are having just one electrons, so that it is going to have a hydrogen-like behavior. Hydrogen-like behavior. Okay, that's very natural to understand. And so the energy is going to be mR over m. And dielectric constant square and n square, that is the hydrogenic quantum state, and then the hydrogen energies. And here the basic ground state of the hydrogen, and that is 13.5 electron volts. And the MR is it's called the reduced energies, reduced mass, and 1 over mR is electrons plus 1 over m whole. In other words, the effective mass in the conduction band and effective mass in the valence band, and then it's averaged out like in this fashion, and then we call that the reduced mass, and then that should be used for that. Okay, the imperfections. We are going to have many different kinds of imperfections in a solid, right? And imperfections, dislocations, grain boundaries, and void, even cracks, whatever. We are going to have many different kinds of micro imperfections. And imperfections, the alpha is going to be about 10 to the third. Typically, it's less than 10 to the third. Okay? And the alpha imperfection absorption by the imperfection, it is proportional to the optical cross-section and the density of the imperfections. It's as simple as that. And the optical cross-section is typically 10 to the 16th per centimeter cube, centimeter square. Okay? And retrostraling observation, we have seen this. We have discussed about that already. That's a resonance of the phonon and the photons. Now, the free carrier absorption, which is important in a metal case, this free carrier absorption is the alpha is proportional to the lambda wavelength and nth power, and that n is typically from 2 to 3. Okay, it's going to increase with something like this in the curve. Now, in order to understand the free carrier absorption in a metal, you have to work with the now the phenomenon itself is going to be something happens in the conduction band, and then the electron is going to be filled. This is the typical metals. Of course, you have a valence band, and then the electron is going to be filled in the valence band. But the conduction band, it has to be partially filled so that this electron can move to the empty states, which has a separation. The energy gap is like 10 to minus 12. That's small. So we just thought it's a continuous band, right? And then this, with the hopping of electrons to the next nearest empty states by observing the light light energies, that is going to be called the free carrier absorption in the metals, by free carriers. And to this, strictly speaking, this transition will going to change in delta K, not only the delta K, but also in a delta E by the absorption of the energies, even though this delta K is not significant. It's going to be very small compared to the indirect transition band, in transition case. But it does have a change in the phonon wave numbers. Okay? So if you want to look at that absorption, now you start with the alpha. You remember the absorption constant is related to the conductivity and refractive index. Okay? You have to remember this. So if you want to understand the absorption constant, you have to understand the dependence of sigma and gamma with respect to the frequencies, right? This frequency is related to the h bar omega photon. In this way, it is related to the energy of the photons. So with the energy of photons, light energies, the absorption constant is going to be changed. And then if you want to understand how the absorption constant is going to be changed with the light energies, then you have to understand how the sigma conductivity of the material and refractive index of refraction is going to be changed with the frequency of the light, which is the main thing for the to determine the energy of the light, right? So basically what we try to do is we want to understand the change in the sigma conductivity of the material and the refractive index of the material with respect to the light energies. In other words, the frequencies of the light, electromagnetic wave. So in order to do that, what you are going to do is we are going to set a classical equation for electrons with electric field which has a frequency like e to the minus I omega t. Okay? And then that equation is the velocity of the this is actually the acceleration. We are going to balance the force of the force equation, and you have to have a Newtonian MA to get this force on the left-hand side, and then velocity with the tau, that is the damping. This is the damping. This is the force MA, okay, damping factor. And that should be related to the electric field, e t minus I omega t. That is a force balance equation, actually. This is a force balance equation, right? And the tau is the average time between the scattering event. We have seen that, right? It's accelerated for the time t, for the time tau, right? And since the Vx velocity is going to change with respect to proportional to the electric field change, in other words, with the frequencies or something like that, you can solve this. You can arrange this to 1 over tau and Q over m E star E electric field e to the minus I omega t, something like that. Okay? And then solve for the Vx. Solve this equation for Vx. Now finally, Vx now is equal to something minus Q over me star electric e to the minus I omega t. That is the change in the electric field. And this thing should be multiplied with tau 1 plus omega square tau square plus I omega tau square 1 plus omega square tau square. That is going to be the Vx, okay? And the flux is going to be nqVx, which is equal to the conductivity complex, if it is a complex variable, you should write a star on this, minus I omega t, okay? So that you can have this sigma value from this Vx with this equation. Then you end up with sigma is equal to nq square over me star times tau 1 plus omega square tau square. This equation is beautiful. It just shows us how the conductivity of the material is going to be changed with the frequency of the light. Okay? In other words, with the energy of the light energies. And then we have this equation, and then sometimes it's going to be sigma dc. This is the dc sigma value, and then wait a minute. 1 over plus omega square tau square. You remember that the mobility is me star over q, the relaxation time, something like that, okay? CF. And the conductivity is going to be nq mu. So if you remember this and then put it into this, then you end up with something like that. So if you have this, once you have this, then you can distinguish 4 different situations in this metal free carrier absorption. Number 1 is low conductivity. It's typically semiconductors and insulator or whatever. And then the low frequency, the light energy is low. Okay? Low, how low is omega tau in that equation is less than 1. And for that, omega is less than 10 to the 12 second. Okay? In that case, we call that the frequency, the light energy is low. In this case, we know that the refractive index is square root of a dielectric constant. We have to involve the permeability of the material, but in the optical range, the permeability is always close to 1. So we just take that out. And the sigma is going to be sigma dc, because the low frequencies means it's almost a DC, direct current, not alternating current. So the alpha is going to be 4 pi over c, 1 over square root of the dielectric constant, and the conductivity, I'm sorry, and this DC conductivity is not a function of frequency anymore when the frequency is very low, so that we can conclude that in these materials, the absorption constant is not a function of the light energies. It's not a function of light energies. I should emphasize on this. Okay? That is one case. And the number 2 case is low frequencies and high conductivity, like a metal. Then what happens? The gamma now is going to be refractive index. It's going to be omega. All right? You remember we had R square is going to be dielectric constant plus C square R square over 4 pi or 4 omega square. We have this equation. Okay, from that equation, if you have a low frequencies, high sigma, then you can write the R is going to be something like this, okay? So the alpha now is going to be 4 pi over C sigma dc over square root of 2 pi sigma dc over omega, something like this. And then that is 4 pi over C root 2 pi root omega sigma dc. Okay? And then that is 8 pi over C square omega sigma dc. Something like this. This means now the absorption constant is proportional to square root of frequency of the light. Okay? That is different from this case. And in this, if we have a skin effect in a metal. Skin effect means everything is going to be reflected on the surface. Okay, that is going to be called the skin effect. Skin effect happens in the high conductivity materials like metals. Now alpha is going to be sigma dc and omega, and alpha here, just like this, alpha is going to be proportional to the square root of omega. Here, just we have then seen this. So in a metal surface, the absorption constant becomes very high with high sigma values and high omega values, high frequencies in the high energy, light energies, which means absorption happens on the substance surface. On the substance surface, every absorption, the light is going to observe in the surface, which is the same thing to the 100 reflections for the conservation of energies. If the energy is going to be observed on the surface, it means that everything has to be reflected. Okay? So that is going to be called the skin effect, and that happens when you have a very high conductivity, high light energies. Number 3 is the high frequencies. In other words, the omega tower now it is greater than 1. and then a low conductivity. Okay? Then in this case, sigma is going to be nq squared over me star tau 1 plus omega squared tau squared. It's going to be omega dc over omega squared. Okay? So alpha is 4 pi over c sigma over r. Now it is sigma dc over square root of dielectric constant and 1 over omega squared, which means now the absorption constant is now proportional to the lambda square. Okay? Inversely proportional to the omega minus 2 power. And then finally, we can think of one more case where the high frequencies and high conductivity now sigma is going to be proportional to the omega and tau, just like that, okay, in this case. You just put in the first equation there, then you'll find this. And then R, refractive index, is going to be proportional to square root of sigma over omega, and then that is times something like this, right? So it means that omega minus 3 and tau minus 1 power. And alpha is proportional to sigma over r, as you have seen here, so that alpha now is proportional to omega minus 2, tau minus 2, and omega 3 halves and tau, right? And this is omega minus 1 half, tau minus 1. So this means now alpha is proportional to the absorption constant, proportional to 1 over square root of light frequencies. So we have seen 4 different cases. The first case, light absorption constant is not depending on the light energies. In the second case, the absorption constant is square root of light energies. Its absorption constant is proportional to the square root of light energies. In the third case, the absorption constant is inversely proportional to the light energy's second power. And finally, we have seen that the absorption constant is proportional to the square root of, inversely proportional to the square root of light energies. So depending on the situation, we're going to have a different free carrier absorption. And that has been summarized in your textbook as a table. In a table, it looks pretty complicated, but in this class, I just summarize the essential part, and then that is important to see, okay? All right, on Wednesday, we are going to talk about the photoelectronic effect, and then wrap up the optical properties in chapter 8, and then we begin to discuss about the electrical properties, which is the main chapter in this whole lecture. Okay. We begin to study in this in the next lecture. Okay, I'll see you on Wednesday then.